reference. Okay, so the exam is 50 questions. It's multiple choice and matching.
Okay.
No short answer, I don't think.
Okay.
And it covers, basically the first four sections of the course. So sizes and units, along with scientific notation. So know about how big things are, roughly how big is a galaxy compared to a cluster, compared to a planet. Scientific notation, you should know about that as well. And then Kepler's laws, right? The laws that govern the orbits of things.
Yep, I have those.
Yep. And then Newton's law of gravity. So the inverse square law is important too.
Yep.
And what that's saying is if you take two objects and you move them twice as far apart, then the force between them goes down as 1 over the distance squared, or a quarter as much.
Okay.
That makes sense. So gravity gets weaker with distance and stronger as things get closer.
Yep.
Gravity also depends on mass. So if something is twice as big as something else, it's going to have twice as much gravitational force between them. Those are two important factors with the law of gravitation. Let me get the study guide here, so people can see. And let me see how to share the screen. Share screen, and we'll do this one here. Okay. So gravity, fundamental forces. So just to review what those are, the four fundamental forces are gravity, the electromagnetic force, the strong force, and the weak force. So gravity, of course, governs the gravitational attraction between objects. Electromagnetism governs light and magnetism, and also electricity. Strong force binds the nuclei of atoms together, and the weak force has to do with radioactivity. So in this course, we'll mostly focus on electromagnetism and gravity.
Right.
Okay. Any questions about this first part here? Size and scale, forces, orbits. Pretty straightforward. Now, we spent a lot of time talking about light, because light is very important in astronomy, because it's the main way we know what the universe is made out of. So, know about the different kinds of light, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. Which ones have the most energy? Remember that energy for light is related to frequency. High frequency light has the most energy. So gamma rays have a higher frequency, so they have more energy than radio waves, which have a lower frequency. Also, if you look at the next line here, no matter what kind of light it is or what kind of energy it has, it all travels the same speed. All forms of light travel the same speed. So more energy for light doesn't mean it travels faster. They all travel the same speed. Objects emit light, this next line here, because of temperature, and the kind of light that something emits depends on its temperature. The hotter something is, the bluer the light that gets emitted, or the shorter the wavelength. So something that's very hot will be blue hot, right? So stars which are hot are blue, stars which are cool are red, right? And then stars which are in between, like the sun, would be yellow. So color in astronomy tells us temperature.
That's another question that I had. So, I think one of the questions for the star part was which kinds of stars are the brightest, and I think I had put down blue stars, but I think somewhere else it said that red stars are brightest, so I got a little confused there.
So that's a really good point. How bright a star is depends on two things. It depends on temperature. So in that case, blue stars would be hotter. And it also depends on size. So a star can be relatively cool but very bright, like a red giant. So a red giant star is relatively cool, but it's an enormous star, so it appears very bright. So how bright a star appears depends on two things, temperature and size.
Okay.
Right, so you can have a small, hot blue star be the same brightness as a large, cool red star. Right. Just because there's two factors that go into that. Yeah.
And that's apparent brightness, correct?
That's apparent brightness, yeah, that's right. There's also intrinsic brightness, which is luminosity, which is related to size and temperature as well. Apparent brightness depends on distance. intrinsic brightness or absolute brightness is luminosity, which doesn't depend on distance. Okay, so we'll get to that. Different phases of matter. Just remember, as things heat up, they go through different phases. So it goes solid, liquid, gas, and then the hottest phase of matter is plasma. So stars like the sun are made out of plasma. They're too hot to be gas, too hot to be liquid, too hot to be solid. They're plasma. And that's all I want you to know about that. Nothing beyond that.
Okay.
We also explored telescopes. Remember the two basic types. There's reflecting telescopes, which is mirrors, and refracting telescopes, which is lenses. And the main purpose of a telescope is to collect as much light as possible and bring it to a focus. Both telescopes do the same thing. They collect light and gather it together. It's just the design that they use. The second question here, what does the light gathering power of a telescope depend upon? It depends on the size of the mirror or lens.
Mm-hmm. Okay.
So larger telescopes collect more light.
That question I struggle with a bit. I'm not sure, looking for it in the book. I think one of the questions it asks is how much the diameter, something about the diameter, how much light it collects, or how much how much bigger it is, or something like this. But I struggle with that.
Yeah, I can see why, because it's not just the size of the mirror, it's actually the area of the mirror. So remember, area goes as pi times the radius squared. So if something is twice as large, if it has twice the size of the mirror, it's going to collect 4 times as much light. If it has 3 times the size of the mirror, it's going to collect 9 times as much light. It's a little confusing, but it goes as the area of the mirror, not just the diameter. So that question that you're referring to is referring to that. So if something is twice as large as another telescope, it collects 4 times as much light. Yeah, that is a little tricky and takes some practice. Go ahead, Sydney.
I was just going to say the types of telescopes that most observationists use would be reflecting telescopes. That's what I got.
Yeah.
Is that okay? Because they're lighter on top and they see the electromagnetic spectrum. Like that's kind of what I have written down.
Yeah, and the main reason is you can build a much larger mirror than you can lens. Just because you can support the mirror from the bottom, whereas a lens needs to be in a tube to support it. And the largest telescopes with lenses eventually begin to sag under their own weight because the lenses were too heavy. So larger mirrors can be lighter and bigger than lenses. So the largest telescopes, including the Hubble, is reflecting telescopes. We use mirrors. Good. Any other questions about telescopes? Spectra are very important. They can also be very confusing. Remember, there's different types of spectra. There's a continuous spectrum, which is like a rainbow, and that's produced by an object at a certain temperature. So the spectrum of the sun looks like a rainbow. The brightest part of that spectrum is the temperature. So the brightest part of the sun's spectrum is in the yellow-green part of the spectrum, and so that's temperature. The red star would have a rainbow spectrum, and the red spectrum would be in the red star. So the red would be brightest in that rainbow. The white star would have a rainbow spectrum, but the blue would be the hottest. So that's a continuous spectrum. Now, an emission spectrum is produced by a hot, thin cloud of gas. So if a gas cloud gets heated up, it emits certain wavelengths, and those wavelengths can tell us what that cloud is made out of. Absorption spectra are similar in that light from a continuous source, like a rainbow, is through a cooler cloud, and certain lines get absorbed by the cloud. The lines which get absorbed should also tell us what atoms are in that cloud. Okay, so any questions about the different types of spectra? Okay, so it's a little confusing at first, but if you work out, what's actually happening, it's much clearer. The important thing about spectra is that they give us lots of information about the objects. They tell us composition, they tell us temperature, they tell us velocity, they tell us direction, surface gravity, all kinds of information can be obtained. And then the last part of this question, why do
I read that.
atoms only emit certain kinds of light? Because every atom is different. So the spectrum for an atom is like the atom's fingerprint. It's very unique to that type of element. So hydrogen looks very different than helium, which looks different than sodium, which looks different than iron. So you look at a star's spectrum, you measure the lines in the spectrum, and that tells you the elements that make up that star. So it's pretty amazing that we can tell what stars are made out of. You know, a million light years away, you know what they're made out of from their spectrum. So it's really useful astronomy.
Can you repeat what the spectra tells us again?
Yes.
I have composition, temperature, velocity.
Yeah, composition, temperature, velocity, direction of motion from the Doppler shift.
Okay.
It can tell us about magnetic fields. It can tell us about gravity on the star, all kinds of different things. But the main things for the class is it tells us composition, temperature, and velocity.
Okay. Great.
And then it's important to recognize that hotter stars emit both more light and bluer light. So as you heat up a star, it gets both hotter and bluer. So a star will start up being red, heat it up more, it becomes yellow, it gets even hotter and begins to glow blue hot. So it takes a little practice, but blue stars are hot, red stars are cool. Kind of the opposite of what you would think.
Yeah, that's what I thought. I was like, oh God, and it would never have thought that.
Right, you think, oh, it's red hot. But
Right.
if you take something that's red hot and you heat it up, it becomes orange hot, and then yellow hot, and then eventually you heat it enough and it will become blue hot.
Right.
Right? It's different than our everyday experience, but if you've ever worked with metal, say like a blacksmith, they know what temperature the metal is by what color the iron is. And things get really bright the hotter they get because there's more energy coming out of them. Atoms and energy levels. I wouldn't worry too much about this, but just know that every atom is different on the inside with its energy levels, and that's why different spectra are produced by that atom. Okay, Doppler shift is important because it tells us velocity. If a star's spectrum is blue shifted towards shorter wavelengths, the object's moving towards us. If it's red shifted towards longer wavelengths, then the object's moving away from us. So Doppler shift tells us velocity and direction, whether it's coming towards us or away from us. So it's important for those factors. Questions about that? Yeah, so when an object is moving, the light from that object gets shifted due to the Doppler shift. Excuse me. Okay. Okay, star properties. This is the topic for this week. How do we find distances of stars? Excuse me. One major way is parallax.
Mm-hmm.
And the idea of parallax is that stars which are close to us will appear to shift in the sky more than stars which are farther from us. And the reason why stars appear to shift in the sky is because as the Earth goes around the sun, you see the star from different vantage points. And so just like being in a merry-go-round, that star will appear to shift back and forth a little bit as you go around the sun or on the merry-go-round. So the farther away a star is, the less it's going to shift. So if you can measure that shift, which is called the parallax, you can find the distance to a star. Really useful for stars close to the Earth.
So let me see if I got this right. The further away the star is, the less the shift is.
Yes, exactly. Which makes sense. If someone is close to you and they wave their hand, you'll see it move a lot. But if they're really far away and they wave their hand, you won't see the hand move very much.
Okay.
Yeah. And this works out to maybe 1,000 parsecs, which is like 3,000 light years. So a few thousand light years it works out to. Go ahead. Who else had a question?
I just wanted to make sure that the equation for parallax is distance in light years equals 3.6 times 1 over parallax. Well, parsecs.
Yeah. Yeah.
Okay.
That's exactly right. So basically it's 1 over the angle that's moving gives you the distance. Good.
Okay.
Magnitude, luminosity, and brightness. Well, magnitude is a measurement of brightness, and there's apparent magnitude, which is brightness, which is how bright something appears to be, and there's absolute magnitude, which is luminosity, which is how bright something really is. And remember, how bright a star is depends on its temperature and its size. How bright a star appears to be in the sky depends on its brightness and its distance. So you can have a very luminous star, something that emits a lot of energy, but appears very faint in the sky because it's far away. And you can have a star which is not very luminous, kind of a dim star, appear very bright in our sky because it's very close. So how bright a star appears to be depends on how bright it really is, its luminosity, and its distance.
That was actually another one of my questions. So on one of the homework assignments, it was like the one question that I just couldn't get it right. So it had you place, I think, the distances in order from furthest away to closest to you.
Yeah.
And it was like 100 L sun, 200 L sun,
Yeah.
stuff like that. And like I didn't understand why 100 L sun and 200 L sun was like, it was like supposed to be the same, like the same distance away. Like it was just very confusing.
Well, the way I have to look at the question again, but if something is, 200 times as bright as the sun compared to 100 times as bright as the sun, it'll appear much brighter.
Mm-hmm.
But I think that question is actually referring to the distance too.
Yeah, that's what it was.
Yeah.
It was because of the inverse square law, the whole law is the same.
Yeah. So something that's 200 times as bright as the sun can appear dimmer if it's further away than something 100 times as bright as the sun. So
Okay.
that question is actually relating luminosity and distance.
Okay.
Yeah. Now, the important thing with knowing luminosity and apparent brightness is if you know the two, you can find the distance to a star. So if you know how bright a star really is and how bright it appears to be, you can find its distance. So it's a really useful technique in astronomy. And so one thing astronomers are always interested in is how bright is that star really? Because if they know that, they can find the distance to stars like it all across the universe. Okay?
So they have to know the luminosity and the apparent brightness?
Find distance.
On the distance?
Yeah.
Okay.
Well, 2 out of 3. If they know the distance and the apparent brightness, they can work out luminosity.
Right.
So it's simple algebra to do it. I won't ask you to do it in the test, but just know you can find it.
Okay.
Okay. Let's see. How do you find temperature composition of stars? From spectra.
Mm-hmm.
How does spectral type and color relate to temperature? Spectral type is a measurement of temperature, and temperature determines color. So really, all 3 are equivalent. Spectral type, temperature, and color. Velocity of the star is found with the Doppler shift using the spectrum. Ranges and masses for size of stars. So stars can only be a certain range. You can't have stars which are less than 8% the mass of the sun, 0.08 suns. And you can't have stars which are more than, say, 150 times the mass of the sun. They're just not stable.
Okay.
Okay, so the reason why stars can't be smaller than 8% the size of the sun is there's not enough pressure in their cores from gravity to cause fusion to take place in the cores. Right? They just don't get hot enough to actually fuse and generate their own energy. They can't be bigger than 150 times the mass of the sun because there's too much gravity. The star basically goes haywire, blows itself apart. They're just not stable. So it's
So what was that one more time?
So stars which are larger than 150 times the mass of the sun are unstable, and they basically tear themselves apart.
Okay.
Yeah. So you only find stars in that range of masses. And one thing to remember again and again through this course is mass is the most important factor in a star's life. Larger mass stars burn hotter, they burn faster, they have shorter lifetimes. Lower mass stars burn cooler, have longer lifetimes, and are redder. So everything about a star's life is determined by mass at birth. Okay? And we'll see eventually that what a star turns into and how it evolves depends on mass too. Okay. an important diagnostic tool for understanding how stars relate to each other is the HR diagram, the Hertzsprung-Russell diagram, or temperature luminosity diagram. It's a plot of the temperature versus the luminosity of the star, and you see that stars fall into different categories. There are main sequence stars, there are giant stars and supergiant stars, and there are white dwarf stars. So where a star depends, where a star falls in the HR diagram depends on its luminosity and temperature mass. Okay. Different types of stars. The sun is a main sequence star, and that's a star where it's fusing hydrogen into helium in its core. That's like the main part of its lifetime. We'll see when we study stellar evolution, when stars finish their main sequence stage of their lives, they swell up and become red giants or supergiants. After they finish that stage, they become white dwarfs, or in some cases, neutron stars or black holes. So the different types of stars are different in terms of their temperature and their size and luminosity. Last question here, how do stars' temperatures relate to their sizes? Well, you can have a large red giant star, which is very bright, or you can have a cool red dwarf star, which is very dim. Mm-hmm. Or you can have, a very bright small blue star. So, just remember the temperature and size contribute together to tell you how bright a star really is.
Okay.
Okay. What else? It's a lot of material, I'll admit that, and some of it can be challenging. So I'd recommend having good notes in front of you. Be familiar with the section of the book that the test covers, and just get organized. You've got 75 minutes to take it. Doesn't mean you have to rush, but you have got to be, pretty efficient with your time. Mm-hmm. And it's 50 questions, multiple choice with some matching as well. Okay. Are
your questions similar to the quiz questions?
Yeah, they're pretty similar. They might be a little bit harder in some cases, but if you're doing well in the quizzes, you should do fairly well in the test.
Are there any questions where we have to do any type of like math?
Say the question again, Sydney.
Like, will we have to use some of the formulas that we have here to like figure out an equation and do some math? Because I'm horrible at math, so I'm a little worried.
The hardest math you have to do would be like with the inverse square law.
Okay.
So something's twice as far, it's 1 over the distance squared. Or it might be like parallax. If I say, okay, the parallax of the star is 0.1, what's this distance? Well, 1 divided by 0.1 is going to be 10.
Okay.
That's the hardest question. That's the hardest kind of math to do. So, okay. Yeah, no, it's not going to be anything hard.
Okay, good.
And do you cover parsecs a lot on the test?
Parsecs, not a lot. It's just good to know it's a measurement of distance, like light years.
Okay.
And just, for reference, it's 3.26. Light years is 1 parsec.
Okay.
Yeah.
And I'm sorry.
Go ahead, let's proceed. Any other questions?
To measure the distance between two stars, we would have to use that equation that's like M1, M2 over, that's like I forget what it is, hold on. FG equals G, M1, M2 over G2.
So that's Newton's form of Kepler's third law. And you're not going to need to know how to test.
Okay.
But it's really good to know, because if you know how big the orbit of two stars is going around each other, and you know how long it takes to go around, how fast they go around, you can find the mass of the stars. So it's a really useful technique in astronomy. We'll talk about it more. But it's actually how they found the masses of black holes, is they watch how stars orbit the black hole, and they can use the star's orbits to calculate the mass of the black hole. Even though you can't see it, you can measure its mass.
It's crazy.
It's crazy. So, you don't have to be good at math to understand this, but math is really helpful in astronomy to understand.
Yeah.
Yeah. So as long as you can get the concepts, I'm happy.
Okay.
Any other questions? Melanie, Stephen, you probably learned some things you wish you'd known.
I know some things.
I know.
Nevertheless, I think I did my best. It's just some of the question was kind of difficult to put in place because the way they worded or phrases or something.
Yeah.
You read it, and you know the time was going, so that kept me make me a little bit anxious. So.
Yeah. Well, I think 75 minutes should be a good amount of time, but you've got to be efficient with your time too.
Yeah, I do. Matter of fact, when you read my email, you'll understand.
Okay. Okay. I'll take a look at that.
Okay.
The other thing is, it just didn't work out with my schedule to do the review last night before the exam began. So I'm hoping that, for next time we can do that, just have the review like the day before the exam begins, and maybe more people can join us. But in any case, people will have a recording of this and they can review it before they do the exam too, if they want to. It's just, it's an option.
And by the way, if there's anything that I haven't done, please let me know because this is my first time. I'm trying to do everything I could.
Yeah. Okay. Yeah, I appreciate that. And you can always go under My Grades in Blackboard and look up and see what you completed and see if you're missing anything too. But Stephen, I'll go ahead and check and see if you're missing anything myself.
Where will we find the recording of this?
Good question. Let me think about the best place to put it. In fact, probably I'll put it in the exam 1 folder.
Okay.
Yeah, I was gonna say that'd be the perfect place to put it.
Okay. So I'll go ahead and do that.
Right.
Yeah, I think we're going to run out of time soon because Zoom only gives us 40 minutes.
Okay.
Any last minute questions?
Me, I'm just gonna wait for you.
Yeah, feel free to email me with any questions. I mean, if you're nervous about something before you start the test. If not, good luck. I'll be in touch this weekend about the next week's work. We're studying the sun, which is a really fascinating topic, and it's a great time of year since it's so sunny out. By the end of next week, you'll know why the sun shines, how hot the sun is, the different layers of the sun.
Actually, I already did that week as well, so I know.
So you can tell us all these things. So when you go to your 4th of July barbecue, you can tell people why the sun's shining.
Yeah.
Most people won't know that. You can actually quiz people.
I just wanted to know. I just thought of it. So after we finish the test, will we be able to go back and review our answers that we had given?
I can't remember. I think you can, but I would say before you submit the test, you may want to save a copy of the test and the answers.
Okay.
You can either do a print screen or copy and paste it into a new document.
Okay.